This video will cover the malonic ester synthesis. The malonic ester synthesis uses an ester of malonic acid. Therefore, a malonic ester looks like this. A malonic ester is a beta-dicarbonyl compound. Remember that beta-dicarbonyl compounds have very acidic alpha protons, which can easily be deprotonated to form the enolate, which can then be alkylated or acylated. The malonic ester synthesis takes advantage of the acidity of the alpha proton. The malonic ester is first deprotonated with a strong base. Remember that, just like with the Claisen condensation, we want the structure of the base, the R group, to match the structure of the ester, R group. Next, the enolate that is formed is alkylated. This produces the alpha-substituted malonic ester. This alpha-substituted malonic ester is then treated with aqueous acid and heat. Remember that treatment of an ester with aqueous acid causes hydrolysis of the ester. This produces the alpha-substituted malonic acid. Carboxylic acids with a beta-carbonyl, such as this one, can easily be decarboxylated. In other words, the carboxylic acid portion is removed to form a substituted acetic acid. Notice that we call this a substituted acetic acid because the product is acetic acid substituted with the R prime group that we added in the second step. We will break the malonic ester synthesis mechanism down into 3 steps. First, the formation of the enolate and the nucleophilic addition of that enolate to an electrophile. Second, we will consider the ester hydrolysis portion of the mechanism. Note that the mechanism for this portion is exactly the reverse of the Fischer esterification mechanism. Finally, we will consider the decarboxylation mechanism. One final note: the identity of the ester R groups is inconsequential since they don't show up in the final product. Therefore, we will continue to use R to designate these groups since their identity is unimportant. First, we will consider the formation and nucleophilic addition of the enolate. Remember that the alpha protons of beta-dicarbonyl compounds are very acidic. Therefore, treating them with strong base results in the conjugate base. The enolate ion. The enolate ion is resonance stabilized. This enolate is nucleophilic and can react with an alkyl halide in an SN2 mechanism to produce the substituted malonic ester product. Next, let's consider the ester hydrolysis step. In the ester hydrolysis step, the substituted malonic ester is treated with strong aqueous acid and heat to produce the substituted malonic acid. The alcohol of the original R group is also produced. The mechanism for the hydrolysis of an ester in aqueous acid is exactly the reverse of the mechanism of the Fischer esterification. In the first step of the mechanism, one of the carbonyls is protonated. The protonated ester is resonance stabilized. Next, water attacks to produce the tetrahedral intermediate. Proton transfer turns the alcohol into a good leaving group. The leaving group leaves, producing a resonance-stabilized carbocation. Finally, water deprotonates. To produce the neutral carboxylic acid. This mechanism is then repeated with the second ester to produce the substituted malonic acid. The final step of the malonic ester synthesis is the decarboxylation reaction. The decarboxylation occurs in aqueous acid and heat, just like the previous hydrolysis of an ester mechanism, to produce the substituted acetic acid. Carbon dioxide is also produced. The decarboxylation reaction is a special reaction commonly seen in beta carbonyl carboxylic acids. In other words, carboxylic acids that have another carbonyl at their beta position. This is because this type of compound can attain a conformation where the beta carbonyl compound can act to deprotonate the carboxylic acid. Notice that I have just redrawn this compound so that the carboxylic acid proton of one carboxylic acid is near the carbonyl oxygen of the other. The carbonyl can then easily deprotonate the carboxylic acid, removing CO2 and producing the enol. The deprotonated carboxylic acid is lost as carbon dioxide, leaving behind the enol of the other carboxylic acid. This enol is then protonated to produce a resonance-stabilized carbocation. In the final step, the protonated carboxylic acid is deprotonated to produce the substituted acetic acid product.